Hello everybody, I'm Christopher Diekmann from Culture Institute of Technology, and I'm going to talk about stable isotopes and tropospheric moisture and about how the measurement from space-based remote sensing can support atmospheric water cycle studies, here with special focus on West Africa. I'd like to start with a statement from the European Space Agency, which highlights the importance of water vapor as a key component of the Earth's hydrological cycle, critical in shaping the global environment and supporting life on Earth as we know it. This becomes particularly clear in the example of the semi-arid Sahel zone in West Africa. During winter times, the Sahel zone, which is marked here by the red box, is dominated by northeasterly trade winds that transport extremely dry air masses from the Sahara into the Sahel. As contrast, during summer, the so-called West African monsoon sets in. Here, southwesterly winds penetrate moisture from the tropical Atlantic into the Sahel and generate here heavy rainfalls, accounting for more than 80% of the yearly rainfall in this box. This extreme yearly cycle pushes even modern climate and weather models to their limits, leading to poor seasonal and daily weather forecasts for the Sahel. This makes clear that new methods for describing and investigating the atmospheric water cycle are urgently needed. A very promising approach that has developed in recent decades is the analysis of the isotopic composition in water vapor, which allows for unique insights into transport and microphysical processes of atmospheric moisture. So first of all, if we talk about different water isotopes, we mean water molecules that differ in their isotopic composition. H2O is the most common and most abundant water isotope. And if one hydrogen atom is replaced by a heavier deuterium atom, then we obtain HDO. Due to the increased molecular mass, some physical properties change. For instance, the saturation vapor pressure reduces, what has a significant effect on phase transitions and therefore leads to fractionation. In this case, lighter isotopes evaporate preferentially and heavier isotopes condensate preferentially. The common notation for HDO is the so-called delta D notation, which relates a given ratio of HDO to H2O to a standardized reference ratio R5mol. In this way, delta D is given in per mil and ranges from -1000 per mil if there's no HDO at all, and reaches 0 per mil if the HDO-H2O ratio equals the reference ratio R5mol. Typically in the tropical metroposphere, values around -300 to -100 per mil are observed. But why is it now interesting to investigate delta D in addition to H2O? Well, on the left, we see a global distribution of H2O in the mid-troposphere measured from space. And for these indicated specific regions, also the corresponding delta D are visualized here on the right. Here, the H2O values of these four regions are plotted against delta D, resulting in the four different scatter points for the four chosen regions. For instance, if we compare the data over Alaska with those over South Africa, then we see that both regions show rather similar H2O values, but completely different delta D values. And over the Atlantic, we observe rather constant delta D values, but a huge spread in H2O. The reason for this is that these regions are largely dominated by very different moisture processes, which create characteristic and unique imprints in the pairwise view of H2O and delta D. And in turn, the analysis of such H2O delta D structures allows to draw conclusions about the prevailing moisture processes in these regions. I'd like now to demonstrate how these characteristics can support the analysis of moisture processes during the West African monsoon. For this purpose, my approach is to first generate a novel set of tropospheric data from H2O and delta D by using observations from Metopiasi, and then to add additional model data and interpretative frameworks in order to identify the major processes controlling the moisture budget over West Africa. Here, this figure on top lists all available and reference data sets of H2O and delta D from space-based remote sensing. It becomes obvious that there is a large lack of continuous daily and global datasets of water isotopes from space, which we now filled with our novel Metopiasi dataset shown in the last row. Using METOP-Yasi spectra for such purposes is in particular interest, as this sensor will be carried also on board the next generation of METOP satellites, at least for the next 20 years. Therefore, we developed in our group during the last years a quasi-operational processing chain, which takes the Yasi level 1 and level 2 data provided by EUMETSAT and performs a line-by-line retrieval with additional post-processing steps with the aim to create pairs of H2O and delta D. By applying this processing chain, we processed all Yasi data between late 2014 and end of 2020 and generated global maps of H2O and delta D twice a day with around 300 to 400,000 high-quality data per day. To give an impression of the wealth of data, I plotted here on the left all data points from 2015 to 2018 over the Sahel for the months February, May, August, and November. In order to better visualize the structure of these massive data point clouds on the left, I summarized each of those with two-dimensional histogram contours, like shown here on the right. For instance, the February data are summarized by these two blue lines, where the thinner line indicates the location of the main 90% of all data points, and the thicker line, the main 50% of all data points. In that way, a very clear yearly cycle becomes apparent. During February, there's a strong correlation of H2O and delta D, with ranging to very dry and low H2O and delta D values, whereas during August, very high H2O values go along with a rather decreasing delta D. So the question is, what is the reason for this anti-correlation during summer? Or in other words, which processes occur during summer and winter that account for this observed seasonality? The assumption is that the increased rainfall during summerly monsoon period might be a reason for explaining the anti-correlation between H2O and delta D. To follow this assumption, we take a deeper look into a typical convective cell from the West African monsoon, like shown here, and plot it together with the moisture processes that are associated with such a so-called score line. The moisture input into this convective system is shown by the blue arrows, where water from surface evaporation and moist advection is injected into the convective updraft. Then here several microphysical processes like rain condensation and evaporation take place, indicated by the green arrows. The trailing stratiform part of the cell is marked by the synoptic scale rear to front inflow, which is marked here in red. This feeds dry air below the stratiform shield and induces here strong rain evaporation. This goes along with an evaporative cooling of the surrounding air masses and creates subsidence such that these downdrafts reach again the convective updraft. The question is now, how do these individual processes reflect in the H2O delta D phase space? And since H2O delta D data from METOP-Yasi are only available for cloud-free conditions, how can we investigate the effects of these rain processes? For this purpose, I considered theoretical frameworks from Noon 2012, and based on that, we were able to show that the effects of such processes can be described by idealized process curves, as shown here with the arrows in the same colors as in the previous slide. Let's start here with the left plot. Here, the effect of air mass mixing is described by those hyperbolic curves. In particular, the blue one for moist air mass mixing, and the red one for dry air mass mixing. And if we zoom into this solid black frame, we get the picture on the right, where the effect of microphysical processes is shown. For instance, the case of Rayleigh rain condensation creates signals shown by the dark green Rayleigh line. And if in addition to rain condensation also rain evaporation occurs, then the slope of the Rayleigh lines increases and we obtain the so-called super Rayleigh lines shown in light green. With additional backward trajectory analysis, we were able to provide evidence that these lines indeed have the capability of reliably describing H2O delta D variations over West Africa. However, as this would exceed the limits of this presentation, I will keep the next slide only as reference. I will instead head over to the application of these process curves for the analysis of the METOP-Yasi data over West Africa. For this purpose, we will go back to the H2O delta D seasonality as discussed previously in the previous slide. is shown here in the left, but now I underline these Yasi data with the theoretical process curves for air mass mixing and the microphysical rain processes. And it becomes apparent that there's a great match between the Yasi data and the theoretical process curves. For instance, during February, when air is transported from the Sahara into the Sahel, the blue H2O delta D contours shows extremely dry signals and strongly follows the hyperbolic mixing lines. And during summer, the monsoon conditions prevail, and as response to these moist northwesterly winds from the tropical Atlantic, the H2O values of the red H2O delta D contour are very high, shown here in the red, whereas the anti-correlated decreasing delta D here appears to follow the super Rayleigh line. And therefore, the suggestion is that the increased rainfalls are the main driver for that anti-correlation, which finally leads here to these signals as shown in the red contour. This suggests that indeed these simple theoretical process curves are a promising framework for interpreting and understanding H2O delta D distributions. In the next slide, we will go more into detail by showing an example of how such relations may be used for an improved process identification. Here I used rainfall data from the space-based remote sensing product GPM IMERGE from NASA to perform a rain event clustering for the monsoon period 2016. I identified all days that were either not affected by any convective events at all, representing the non-rain events here on the left, or all days that experienced heavy convective events, representing the post-rain events shown on the right. And then I separated the METOP-Yasi H2O delta D data according to those two event classes and obtained following H2O delta D contours. The blue contours show the Yasi data for the non-rain class, and the red one for the post-rain class. And in fact, we again observe the clear separation into mixing signals if there's no influence of rain, and into the super Rayleigh signals if the observed air mass was indeed affected by convective rain. And this confirms that even by simple theoretical frameworks, such observation-based H2O delta D distributions can be understood very well in terms of their underlying processes, with each having a unique effect on the two-dimensional H2O delta D distributions, something that would not be such clear if only looking at H2O. As a consequence, such characteristics provide various opportunities for process identification studies and for evaluation of observational datasets, as just shown for the Yasi data, but also for the evaluation of atmospheric weather and climate models, which incorporate the water isotope fractionation physics. For instance, by using the isotope-enabled models ICANART-ISO and COSMO-ISO, we were able to evaluate different model settings and their effects on the simulation of the West African monsoon, and could show that adding information about delta D provides deeper insights about the behavior of a model, which would not be possible by only looking at H2O. And with that, I would like to come to my conclusion. At first, I created a novel dataset of tropospheric H2O delta D data from space-based remote sensing by using METOP-Yasi data, which is currently unique in terms of spatial temporal resolution and coverage. In a second step, I added theoretical frameworks to better interpret H2O delta D distributions over West Africa. And in the final step, I aimed at a synergy of the satellite and model data in order to investigate the H2O delta D variability over West Africa and to understand the major controlling mechanisms. With that, I was able to identify the major processes controlling the mid-tropospheric moisture over West Africa. As summary, I could demonstrate how the careful synergy of satellite and model data can support the analysis of the isotopic composition of tropospheric water vapor. Such a study covers an invaluable potential for improving the understanding of the atmospheric water cycle and for contributing to the improvement of our weather and climate models. An example of how the water isotopes from METOP-Yasi can improve the numerical weather forecast is given and discussed, for instance, in the talk of Farah Khosravi. And with that, I would like to thank you very much for listening.